Howdy, and let's begin reviewing for topic 1.3. That would be stoichiometry and gas stoichiometry. So this can be a little tricky if you're not following the same basic principles and you're not on your toes. So be careful. Now, number one is asking us that zinc metal reacts with copper 2 sulfate according to the following equation here. So zinc, this is an oxidation reduction reaction, right? And we want to determine the mass of copper that can be deposited when 1.7 grams of zinc is added to 50 milliliters of whatever that is, molar copper 2 sulfate. So we have zinc, copper sulfate, and then zinc sulfate and copper. Now we know that we have 1.20 grams of zinc, and then we know that we have 50 milliliters. Remember, that's just milliliters. 2.00 times 10 to the minus 1 molar. 2.00 times 10 to the minus 1 molar. That's a complicated way of saying 0.2. And then we want to know how many, let's see, the mass of copper. So how many grams of copper. So you may you may just pick the first one and say, okay, I'm going to go this, but the first step is going to be to define the limiting reactant. Okay. And you will get these. They will happen. So what you should do is you should take both of your reactants, and you should find them in moles. So we're going to convert 1.2 grams of zinc, and we're going to convert to moles. And I looked ahead, that's going to be 65.4 grams per mole. And then that will be 0.0183 moles of zinc. And then I need to find how many moles of copper sulfate were available. So I will start with 50 milliliters of copper sulfate, and I will change milliliters into moles. By moles over milliliters, hey, you could have written molarity as moles over liters, right? Well, moles over liters, moles over milliliters can look the same if you put 1,000 in front of milliliters and then put your molarity to 2 times 10 to the minus 1 on top of it. That will come out to 0.01 moles of copper sulfate. Now, since this is a 1-to-1 ratio, that means that 1 mole of zinc and 1 mole of copper sulfate will react at the same time. Then in that same ratio, we'll just choose the lowest number. So this guy is my limiting reactant. Okay, so that's the one I do calculations with. And so I will take 0.01 moles of copper sulfate. And if you can predict the future, you can see that the mole ratio to copper, from copper sulfate to copper, is a 1-to-1 ratio, because that's a 1-to-1 ratio. And then I want to find the mass of copper, so I'll just go ahead and add that conversion factor, moles to grams of copper. And that's going to be 63.5. And I will end up with 0.635 grams of copper. Okay. Piece of cake. Now, for number 2, it's kind of the same thing. We want to calculate the mass of carbon dioxide produced when 150 milliliters of 1 molar hydrochloric acid is added to 10 grams of calcium carbonate. You should remember this from your acid-base unit, because this is an acid-base reaction. This is our acid, and this is our limestone, right? So that was kind of similar to the acid-rain equations as well. So we have limestone in our aquifers. If we get too much acid in it, it will erode the aquifers. So if we have HCl and reacts with calcium carbonate, we have to make our own equation. Now, since it's an acid-base reaction, we usually end up with salt and water. Now, you hopefully remember that your products for this were CO2, water, and then we also need that calcium, and we need that chlorine to throw in there, and the calcium chloride. Okay? Now, calcium is a 2+, and then chlorine is a 1-, right, charge. So that's why we need that 2 right there. So if you can tell, we also have two hydrogens here, but our equation's unbalanced. So this is why they want you to write your own equations. Usually they'll give you simple ones, kind of like this, or ones that you've seen multiple times. But they want to make sure that you can balance it right here, because that's going to be a key factor in a second. So we had 150 milliliters, and we had 1 molar solution of HCl, and then we have 10 grams of calcium carbonate. So again, we need to find the limiting reactant, okay? Because the reason why is because we have two different reactants, and we have the masses of 2 reactants. We will run out of one first. If you only get 1 reactant, like the next question we're going to do, then that's your limiting reactant. Just move on. But if you get 2, you're going to have to do this. Okay, so always keep your head pulled out for that one. So again, we'll go by the same rules. We'll just take our grams of calcium carbonate, and we'll convert it to moles. And now, fun fact, calcium carbonate has a molar mass of 100. That's why we like to put it in our exams, because it's easy. So you may want to remember that. You will probably see that on your test. So that's 0.1 moles of calcium carbonate. Okay, and then we will take 150 milliliters of HCl. We need to find out how many moles is in here. So I have my volume, and I will multiply by my molarity. Now, this is moles per liter. So this is moles per, I need to make this liters, so I need to make 1,000 milliliters. So that is going to be 0.15 moles of HCl. So now most students will stop and say, hey, okay, I'll just choose the lesser one. That's my limiting reactant. But you would be wrong. This is the excess reactant. Okay. And that's because we have this 2 right here. Okay, we're going to use up twice as much HCl than we are of CaCO3. So a trick here, what you can do is you can do these long drawn out things where you try to figure out which one produces the least amount of product. But what I like to do is whenever I have their molar values, I just like to divide by their coefficient. So here I divide by 1, that's no big deal. But here, divide by 2, and you get 0.075. Okay, so that is the one you should go over. All right, you divide we had to divide by the coefficient that it had in there. So if we have 0.075 moles, I will keep that up, moles of HCl. It asked me the mass of carbon dioxide. Apologize. So we'll just convert moles of HCl into moles of, wait, sorry. Hold on. We had 0.15 moles of HCl available. Okay, this was just to, this number was just used to find the limiting reactant. This is how much we have available. So I should use 0.15 moles of HCl. I'm glad I caught that. So 0.15 moles of HCl is what we had available. and that's what we should go off of. I will convert moles of HCl to moles of CO2. And so that's going to be a 2-to-1. That takes care of that division right here. And then I will go ahead and find the mass of CO2 while I'm at it. Grams of CO2. Another number to stick in your head, molar mass of CO2 is 44. That happens a lot in our equations, so you could remember it or just calculate it. And that ends up being 3.3 grams of CO2. Rock on. Okay. Now, number 3, it says a student prepared ethene by dehydrating ethanol. We'll get to organic chemistry next week. We got the official word. We're closed down for a little while, so we have to just forge ahead. So, first thing when they give you an equation, always just double check to make sure it's balanced. It is, but you never know. They could throw an unbalanced one at you and not tell you. So the students started with 9.36 grams of ethanol, and they made 2.12 grams of that stuff, of ethene. Now we want to calculate the percent yield. So percent yield is going to be the actual value divided by the theoretical times 100. So this right here, this 2.12, this is my actual value. Now the theoretical value we are going to have to find via stoichiometry. What we're going to do is we're going to start with 9.36 grams of ethanol. And we're going to convert grams into moles of ethanol. And the molar mass for that is 46. You can look that up. Those are pretty easy to do. And then we'll change moles of ethanol, C2H5OH, to moles of ethene, C2H4. That's a 1-to-1 ratio. And then we will do convert moles into grams of ethene. Molar mass is 28. Then it ends up being 5.70 grams of ethene. So that was our, let's see, I need a good color. This was our theoretical yield. Okay. That was found via stoichiometry. This one was found via experiment. When they come on test questions, they come just straight into the problem. So we just take 2.12 grams divided by 5.70 grams. I'm losing my pen. Times 100. Times 100. 5.70 grams. And we end up with 37.2% yield. You might get to that number and go, whoa, that's kind of low. I should be perfect. I should be a perfect student to get 100%. No, not going to happen, especially in an OChem lab. This is organic. So 37% yield is pretty good for an OChem lab. I got to tell you, you'll be getting down on your knees thinking thinking whoever if you get that next time you do it in college. So for number 4, it says that a gas sample occupies 67 centimeters cubed at a temperature of 22 degrees Celsius and a pressure of 9.38 times 10 to the 4th pascals. Calculate the volume the gas will occupy at the temperature is increased to 29 degrees Celsius and the pressure increased to 1.06 times 10 to the 5th pascals. Okay. So we see that we have volume given to us, we have temperature given to us, and we have pressure given to us. And we change two conditions, and we're trying to find out that third condition. So this is the combined gas law. PV equals PV. PV over T. P1, V1, T1, P2, V2, T2. Okay? So essentially, we're going to take our pressure, which was 9.38 times 10 to the 4th times 67.2 divided by our temperature. That's going to be 22 plus 273. You got to put it in Kelvin or else it won't make sense. And then we'll get our new pressure here times 10 to the 5th. Now we're finding volume, and then we put 29 plus 273. Once that's done, we will get an answer where x, I assume y'all can solve for x, is going to be 60.9 centimeters cubed. Excellent. So simple ideal gas law, combined gas law equations. Just remember that combined gas law. I don't think it's available on your formula chart. But the ideal gas law is. We should be used to that by now from Chem 1 and also my class. Now the last one is this one. Let's do number 5. We have 2.5 decimeters cubed of gas at a temperature of 19 degrees Celsius and a pressure of 1.01 times 10 to the 5th pascals. Has a mass of 4.59 grams. We want to determine the molar mass of the gas. So here's a heads up. Anytime you see that term, molar mass of the gas, you should probably try to think of density. Try to think of gas density, because this is the way I like to do this little thing. And there's one easy formula you can use that. So if we take the ideal gas law, PV equals nRT, that gives us volume, that gives us temperature, that gives us pressure, but there's no mass in here. So let's see if we can find mass in this. Well, let's just remember that just remember N is going to be the mass of a substance divided by its molar mass, right? Because this is going to be grams, and this is going to be grams per mole. So that's why, and then we have R, and we have T. Why don't we stop for a second when we talk about R? Now, in your data booklet, R is 8.31 joules moles per Kelvin. That's what it says. Now, that's confusing because I tell you that it's 8.31 kilopascals times decimeters cubed moles, not 11, Kelvin. Okay? Or you can just use liters instead. So either one is okay. But notice that this is in kilopascals, which means that our pressure is going to have to be in kilopascals. And also, a side note, if we go back to here, this is in pascals. But if you rearrange this and look at this, if you put this in kilopascals, this is actually going to be 101 kilopascals, which is actually atmospheric pressure. Okay, so that number is worth remembering. That is okay to see. That is not unusual to see 1.01 times 10 to the 5th pascals. Don't freak out. That's atmospheric pressure. That's 101 kilopascals or 100 kilopascals. Okay, Side note. So that's it about R. I'm glad we talked about that because we'll put that in a second. So if we fix this, we had PV equals mass divided by molar mass RT. Let's circumvent that. And so I'm going to move molar mass over to the left, and then I'm going to take pressure and volume and move it over to the right side. Now, you guys are math savvy. I don't have to explain how you do that, but molar mass ends up being on the left, and then we have mass times R times T divided by PV. Okay? And then we have mass divided by volume right here. So if you remember, mass divided by volume is your density. Okay? And R times T, P. So the easiest formula I remember is the molecular weight kitty cat sweeps his dirt over his P, right? So molecular weight kitty cat, his face is, there's the nose, there's the mouth, and then the nose, and then the whiskers, just like that, and his ears. There we go. All right. Anyways, I digress. So that makes this question really easy now. We have our volume and we have our mass. So if we just take 4.59 grams divided by 2.50 decimeters cubed, this gives us grams per liters. Remember, that's liters. This is liters. That's going to give us an answer of, apologize, 1.836. And then so my molecular weight, or my molar mass, is going to be 1.836 times R, 8.31, times T. Sorry about that. Plus 273 divided by our pressure, which is 1.01 times 10 to the 2 kilopascals. So it's got to be kilopascals for this bad boy to work, for the density equation to work, or the ideal gas law to work. You can't use pascals, you have to use kilopascals. So it ends up being 44.1, which is pretty darn close to CO2. Okay? Because remember, the molar mass of CO2 is 44. All right. I hope you all have a good day. I'm sorry about the loud interruption just a second ago.